or should we wait? Should we start?
Yes, sir.
Okay, so let us start because 27 already there. So almost 50% students are here. So yesterday we were talking about drip irrigation system, different arrangements. You recall this? What at the last we were talking about? Different arrangements of drippers. The important aspect here, it was what I told yesterday. In different way we can put the drippers. Simple idea is, this is the area which is allocated for the say tree, a plant. However, we need to only irrigate this area which is shaded one. So you can put number of drippers. Suppose here 4 drippers are required in different form, just like it's a zigzag it is called. Here it is double lateral we have, so both side we are putting drippers. And irrigated area is a fraction of this total area. So in advantages, you have learned that a particular portion it is irrigated, not the whole field. Say 40% or 50% of the total field is irrigated. So that is important in terms of water application and water saving. This particular area is not getting water, so there is less weed relatively, or no weed we can say. So management is also easier. So this is double lateral, we have both sides the laterals, and at a fixed distance we are putting drippers. This is zigzag arrangement. So we have in a square shape all 4 sides of the plant, or all 4 corners we can even say, we are putting the drippers. This is pigtail. In helical form, number of drippers are arranged to supply the required amount of water to the field, and it is called multi-exit. From a single set we have number of drippers arranged here around the tree to supply the water, required amount of water. Rest of the things in the design part of the drip irrigation system, the first and most important is water distribution network. In this we have pump. If you recall, we have from the pump the main line, then different filters, then if it is fertilizer application at the same time, fertilizer injector, venturi basically we use, and then it goes to main line, and from main it is sub main line, and from sub main laterals are arranged, and within laterals we are putting drippers. So in first it is main pipes or main line. So main pipes generally made of PVC or maybe polyethylene, called SDPE pipe, high density polyethylene pipes, SDPE pipes. These are generally 65 millimeter in diameter or even more, and operates under the pressure of 4 to 10 kg per centimeter square. That is required pressure to supply water to each and every meter there. Then after main, it is sub main line, which is distributing water to laterals. So sub main pipe, that is also made of rigid PVC or SDPE, varies from 32 millimeter to 75 millimeter in size, and operates at a range of near about 6 kg per centimeter square. Then it is sub main is usually connected to the main line through a control valve assembly, just like pressure compensating valve, directional flow valve, air vent valve, and so on. So these are all the fittings in water line. Then goes to the lateral, in which either on line or maybe with a tubing, drippers are connected. So laterals, pipe on which drippers are mounted, made of the same LDPE or LLDPE PVC material. generally varies 10 to 20 millimeter inner diameter or in size. 10 is most common, but there is as well 20 for the high discharge requiring conditions. And operational pressure is near about 2.5 kg per centimeter square. As you know that drippers are mostly nowadays we are using pressure compensating type drippers. So operating pressure for the lateral head, it is near about 2.5 kg per centimeter square. But the moment we have number of drippers, maybe hundreds, pressure is reduced. And because these are pressure compensating drippers, so it has no effect, almost negligible effect of varying pressure. At the last, a minimum pressure that is required to operate the laterals, minimum pressure, that is 0.6 kg per centimeter square, or simply 6 meter head of water, near about a little more than that. So minimum pressure head that is required to operate drippers is 0.6 kg per centimeter square, and these are operating at 2.5 kg per centimeter square near about, so that pressure is not reduced than the minimum required condition at the last point dripper is irrigating the plant. Now, after main pipeline, sub-main line, laterals are arranged. These are the valves basically required to control the system or for the safety of the system. Say air release valve or vacuum relief valve. Basically in the pipeline you have already learned in conveyance system design. It is to remove any air lock in the pipeline so that pressure is not increased and that is not damaging the pipeline, main, sub-main and lateral. So at a suitable condition or location, these valves are placed. Air release valve, pressure regulating valve, automatically it controls the pressure. When there is low pressure, it reduces the flow condition or increases the flow condition to maintain the required pressure in the line. Then non-returning valve to remove any water hammer effect. Once pump is closed, water will flow towards the gravity, means if supply side it is at the lower, it will come back or it will go downside with a fast speed that may damage the pipeline. That is called water hammer condition. So non-return valve is basically placed in the main sub-main lines to reduce the chances of damaging pipelines. Flow control valve or on-off valve. Suppose in a main line we have number of sub-mains. So we are operating one or two at a time. So for every condition we have a on-off valve or flow control valve, so that only required laterals or sub-mains are supplying water and rest are at closed condition, so that loss of head or efficient irrigation water application through drip system, it is maintained. Now, pipelines, main, sub-main, lateral, valves arrangement, and then its most important condition is filtration system. Reason being, drippers are very narrow paths to flow the water and supply to the plant or required location drop by drop. So any impurity in the water will clog this or will affect the rate of discharge of these emitters. So especially, though it is most important in sprinkler as well, but in drip irrigation, it is further most important condition of filtering water, very clean water that is required to get supplied. So filtration unit is very strong here. What are different filters and conditions to filter water are to remove any impurities, say suspended particles or debris from the water. So we have the first, suppose it is coming from the surface water body like a river or a pond. There may be suspended particles, certainly, because from the river it is diverted to pump the water. There may be debris, there may be suspended particles. So first what we are doing, we are taking this water to a smaller pond, maybe suppose a long pond. From this side it is water is coming, and after a certain time it is pumped from this side, so that water has sufficient time to settle down any particle which is greater in size or any biological material which can be easily removed by a filtration system. So settling basin is the first condition, which is basically a kind of pond which allows to settle the heavier suspended particles, and it is governed by, simple you have learned, Stokes law. Means it takes some time to automatically settle the heavier particles because of the gravity, size of the particles and density of the fluid, that is simply water here. So settling basin removes large volume of sand and silt that is carried by stream through diversion work, means water is diverted from this river or channel to this settling basin. Minimum size of particle that can be removed depends on the time that is required that the sediment laden water is detained in the basin. Stokes law, from the Stokes law we can find out how much time it will take to get settled. If you recall, in your second year you might have learned to find out sand, silt, clay content of the soil, that is textural analysis, by putting in a jar say 1 liter of certain depth. So if we are mixing well soil with the water and sampling at a particular depth, generally it is 10 centimeter, the water sample, the first sample gives us silt and clay content. After say 24 hours if we are sampling, it will give only the clay content which are suspended. And sand particles are immediately within the first 10 minutes, it is settled down. So in this way, this particular settling basin is designed so that minimum size of the particle, means how much time we have to move the water from here to here, within that time a certain amount or substantial portion of suspended particles will settle in the bottom of this settling basin. So in this way, to achieve best response of this settling basin, its design should be in such a way that it's a long and narrow pond. Long means it takes much time to move from inflow side to outflow side. So long and narrow ponds are preferred as a settling basin to remove any suspended particles quickly, which is following Stokes law condition there. Then second, particles which are not those settled, we need to have a particular filtering media. Basically there is gravel as well as sand media filter it is used. So it is inputting the inflow from this side, suppose, and there is a layer of sand and gravels, water goes below and it is filtered and it is coming from the outer jacket of the tank which is filtering the water, and then it is supplied to the another filter which is substantially after some time supplying water to the drip system. So gravel sand media filter, it is consist of layered bed of gravel, graded sand and gravel that is placed in one or cylindrical tanks. Number of tanks are there is means arrangement so that graded sand and gravels are packed to filter the water for any suspended material that is further coming with the water. And this is essential for primary filtration of irrigation water that is supplied to the drip system. It is low cost because the particular sand it is used and gravel which are easily available we can use. So it's a low cost and easy to operate. Filter media consists of crushed granite, silica or quartz shaped to a specific particle size that is generally varying from 0.17 to 1.22 millimeter. which is arranged inside this sand media filter. So settling basin, then sand media filter, then it is a screen filter. You might have seen in our water filtering unit, household condition we are using like AquaGuard. So it's a screen filter that is fitted in series with basically after this media filter, and it removes suspended solid impurities like sand and dust that is coming along with the water. And size is basically defined by inlet and outlet diameter that depends on the requirement condition to be supplied to drip irrigation system, and that varies from 2 to 30 centimeter in size. And standard mesh size of this screen is generally 100 microns that is taken. So this particular you might have seen in your AquaGuard that is connected from one side, it is inflow of the water and another side it is going out after filtering unit works. So water first goes through this screen, or it is going from the center inside from this inlet, and then it is coming out from the screen, or it is going outside. There are both way. From outside water is supplied and it is pumped out from the center. So these screens are removing certain amount of further suspended smaller size particles of size up to 100 microns. Then it's important, these are all the filters fitted to remove any suspended particles that is in soil. So next is the first, that is basically the primary one. It should be the first, that is hydrocyclone filter. How it works? Water is going inside from the top and it is at high velocity, so it is circulating. So any impurity because of this force flowing or circulating water, it is suspended at the bottom of this tank, cyclonic tank, and then pure water it is pumped or it is taken out from the center of this system that is going to the outlet. So it uses in theoretically vortex motion and centrifugal force to remove suspended means heavier particles, and by centrifugal force they are going simply towards the out or periphery of this jacket and finally settle down, and it has a conic shape. So it is going finally to the bottom where it is removed after a certain time all the sand that is stored or suspended in this particular chamber. So it uses centrifugal force to remove suspended substances with a specific gravity greater than 1.2 or any particle which has higher bulk density than 1.2 gram per cubic centimeter. It is removed by this hydrocyclone or centrifugal sand operated filter. Effective, or it is effectively removes large quantities of sand that is further coming from mesh filter and primary sand and gravel filter. So it is basically first removed from the water and then it goes to sand filter and mesh filter. So this is placed upstream of other type of filter. So this is the first filter. You have not seen it in first arrangement of this figure. If you recall, when I was showing the layout of drip irrigation system, there is a pump, different valves we have, and water is coming say from a canal. So it is first going to hydrocyclone filter, and then it is going to another filtering unit, that is sand media filter, the first you have seen. And once it is going to sand media filter, then after again it is further purified by a screen filter. From screen filter it is basically plate filters. One more filter it is used generally if it is more impurities are there. Otherwise it can go directly to main and sub main to supply the water. So you can see it is main line, then sub main it is full up to the field, and within this we are simply taking these laterals, and in laterals drippers are fitted. The important aspect is here, one more you can see from this layout, that is fertilizer injection in the irrigation water. So we are using Venturi injector, and Venturi is generally placed after hydrocyclone filter, means first level of impurities are removed, then it is fertilizer which is injected, and water along with fertilizer is going to sand media filter, and from there it is going to screen filter, and then it is a disc filter or plate filter, disc filter, and after that 4 level of filtration condition, it goes to main, then lateral, and then main, sub main, and then lateral, and finally supplied water along with this fertilizer to every plant there. So in this way, the first and most important filter is hydrocyclone filter, then it goes to sand media filter, then it is screen filter, and at the last, if further impurities are there, it is basically a disc filter. It removes basically organic material if there are, like algae and other extremely fine particles. So how it works? There are discs, thin discs, which are arranged in a cylinder, and water is going from outside or inside to get removed any of the impurities like algae or very fine particles or extremely fine particles from the water. So it is final filtering component before water enters to the drip line, that is main, sub-main, lateral, and then drips. It contains a stack of grouped ring-shaped discs like this, grouped and ring-shaped discs that capture the contaminating particles in the water. While backflushing, during cleaning of this filter, while backflushing discs are loosened and direction of flow is removed. Suppose it is entering from this side. So to clean this filter is taken out from this jacket. It is loosened so that rings are freely moving, and water is applied or air pressure is applied from this side to remove any impurity which is attached in between these rings or discs. Now, once we have water supply network, filtration units, and control valves, we are now intended to learn designing of drip irrigation system. So design of drip irrigation system basically is the idea of determining system layout, how it will be looking like in the field, number of laterals, how many laterals are required to supply water to cover this whole field, what size of emitter we need to put there so that the required amount of water is applied to the field or to the plants, what size of laterals, sub-mains and main line it should be so that emitters are getting water at required pressure condition to supply the required amount of water in the field, filtration and chemical injection equipment, what size, what rate of injection equipment or fertilizer and chemical injection equipment we should place there, and pumping plant specification means what size of pump it should be there to operate the system at required pressure. So this is the basic idea. Emitter selection criteria, because it's the most important, we need to estimate the discharge, spacing and the type of emitter, whether it should be a pressure compensating or non-pressure compensating. Reason being, it's a cost as well involved there. So what are the major characteristics of emitter which are available? Discharge range variation causes by emitter, that variations within manufacturing tolerance, means it should be within a manufacturing, there is a standard condition. Manufacturing agency or manufacturer is also giving that it may have this level of variation in the operation. So we need to find out which one is satisfying our demand or our need to cater the water in our field. Closeness of discharge pressure relationship means it is pressure compensating or non-pressure compensating condition, means how much it will be uniform under different pressure condition once it is operated in the field. We need to take care about these. Possible range of suitable operating pressure means how much. Suppose it is rated for say 0.6 to 1.5. That is important to know. Reason being, at any condition, it should not be more than 1.5 kg per centimeter square pressure. Otherwise, the results will not be satisfactory. And if it is reduced pressure in the line less than 0.6, that is the minimum pressure required condition, water may not come from these drippers. So all this way, then let's suppose susceptibility to clogging. How much susceptible it is to clogging means whether it is self-flushing kind of, means if there is anything which is coming in between the diaphragm and the outlet of the dripper, whether it can flush automatically at a certain condition when pressure is reduced or increased more than a particular condition. So it is susceptibility of clogging, how much it is self-cleaning kind of condition there. And stability of discharge pressure relationship over a long period of time. With time, there is corrosion or deposition of salt which are usually present in water. So up to what time the system will work satisfactory under a particular condition or water quality constant, that we should know, and that shows simply the stability of discharge pressure relationship over a long period of time. Reason being, when there is a deposition of salt inside the system or inside the drippers, main pipeline, sub-main pipeline, it may not be economical to further operate the system. Otherwise, there may be loss of energy or power there. So these are the conditions before selecting the emitters, or we can say emitter selection criteria based on our inventory of the system, inventory of the area which we are going to irrigate. Now, what I told, this variability, manufacturing variability, it is basically called manufacturing variation. It is measured by supplied means emitters. If we are fitting these emitters in a lateral, and we know that what is the operating pressure of this line, we are taking observations of these emitters, we can find out manufacturing variation. So emitters coefficient, it is also called coefficient of variability or emitter coefficient or manufacturing variation. Basically, it is used to as a measure of the anticipated variation in discharge in the system. That is simply standard deviation divided by mean of the discharge condition of these drippers. But in practical or in estimation, we are simply doing discharge by individual drippers. So Q1 square, Q2 square, Qn square means number of drippers we have taken minus n into average discharge of each drippers square and divided by Q into root n minus 1. So this is the simple idea to find out manufacturing variation or coefficient of variability or manufacturing coefficient of variability of drippers. So S is standard deviation, Q is the average discharge rate of these drippers, N is the number of drippers we have used, and Q1, Q2 and Qn is individual dripper discharge we have observed in our testing observations. So this is manufacturing variation of drippers. Then manufacturing variation that is permissible, recommended range, point source emitters and line source emitter, these two are mostly used. So for point source emitter, if it is less than or CV manufacturing coefficient of variation is less than 0.05, it is excellent system. The moment range is increasing of coefficient of variation, it goes to unacceptable if it is greater than 0.15 of manufacturing coefficient of variation, and in between it is average, marginal and poor. Line source, it is a little more. So 0.1 is good. From 0.1 to 0.2 it is average, and if it is greater than 0.2, then it's unacceptable line source emitters for the irrigation purpose. Then design of emission uniformity or uniformity coefficient we have already learned for sprinkler irrigation system. So emission uniformity is 100, that is in percentage we want to make is 1 minus 1.27 CB, coefficient of manufacturing variability, divided by root n, n is the number of drippers, QM, that is minimum discharge rate for minimum pressure condition, that is rated condition, and QA is average or designed emitter discharge rate, that is given. There are two conditions. We have two set of emitters, point source and line source. So n, if it is a point source, then we can find out these are the number of drippers, n. So n is first case for point source emitter, number of emitters per plant we have put there, just like 4, 5, 1. And if it is parallel line, then for one plant how many drippers are there? 2 in this line, 2 maybe in this line. So in that way we can find out how many number of drippers are there per plant. But if we are putting a line source emitter, then either the routing diameter of the plant, we have routing diameter of the plant, either the routing diameter of the plants divided by the same unit length of lateral used to compute CB, means how much length of this online emitter we have used to compute the CB. Just like here 1, 2, 3, 4. So it is online. So we need to find out how much length we have taken to compute the CB, or simply it is taken as 1. So in this way, whichever is greater we are taking to find out for the root n the value or the condition for uniformity coefficient of a drip irrigation system. Now design emission uniformity. Here we have usually high emission uniformity that is recommended for drip irrigation system, maybe greater than 90, but usually it is taken more than 95. However, there are different conditions. Recommended range in design emission uniformity. Point source emitter for tree crops with a spacing larger than 4 meter by 4 meter. And if there is land slope less than 2%, it is 90 to 95%. If it is greater than 2%, 85 to 90% is also acceptable. Point source, the same kind of emitter for tree club with a spacing less than 4 meter, it is 85 to 90% for less than 2% slope, and greater than 2% slope it is 80 to 90%. However, line source emitters on annual crops for the slope condition less than 2%, 80 to 90% is very fine. And if it is slope of land or topography is greater than 2%, it is 75 to 80%. At any case, it should not be less than 75%, the emission uniformity of a drip irrigation system. Now, number of drippers. How to find out number of drippers we need to put per plant? It is simple idea that percentage of total area shaded by the tree. You might have seen it is located. Suppose it's 5 meter by 5 meter distance. Plants are there, but we are not seeing that this particular plant, it is shading this whole area. So this may be something a percentage. So percentage of total area that is shaded by the tree, maybe 60% or 70% or maybe 80%. Sometimes it is shaded area by this tree. And area per plant that we have length and width, which is assigned, means row to row distance, that is width, and plant to plant distance we can have a length between two plants. So we need to find out the area per tree, and then effective area bedded by the single emitter. How much it is in, maybe in circular pattern, how much area it is bedded by a single emitter. In that way, we can find out number of drippers per plant that is required and area irrigated by dripper, particularly single dripper, that is AI, is spacing between adjacent plant rows or row to row distance, that is L. S is the spacing between emission points or say plant to plant distance, and P is the percentage area that is cropped by the irrigated condition or percentage of cropped area to be irrigated. Just like we are not, if you recall what in the beginning I showed you, if it is arranged in a zigzag path, the total area is something like this, but it is simply irrigating this much area only. So what is the fraction of this total area of that? So this is the basically percentage. Suppose it is a 40% area which is needed to be irrigated, and for this percentage it is divided by 100 to make it is a fraction, and NE is the number of drippers per plant that is required, number of drippers at each emission point, or per plant how many drippers we are putting there. Once you have this clear idea about drip irrigation system, let us understand by a problem. So design of drip irrigation system using following data. Area is same 6 hectare, 200 meter by 300 meter. Water it is pumped from the river near the farm, and level from the field of the river water is 25 meter. Crop is citrus, suppose spacing is 5 meter by 5 meter. Dry climate, effective wind is negligible, no rainfall contribution. Soil type is clay loam, and it has infiltration rate of 10 millimeter per hour. So that is the limiting condition for application rate. ET of the crop, that is peak 8 millimeter per day. No groundwater contribution to irrigation. Root zone depth is 1.5 meter. Field capacity of the soil is 30%. Permanent wilting point is 15%. Bulk density of soil is 1.4 gram per cubic centimeter. And critical point when we need to irrigate is 0.8, means available water is 1 minus critical point, that is 20%. Application efficiency of water is 90%. Lateral spacing is 5 meter, and emitters spacing, because it's a 5 meter by 5 meter spacing between the plants. So emitter spacing is 5 meter. If 1 emitter we are using, it will be plant, means placed at each plant. So emitter to emitter spacing is 5 meter in that sense. And now this is layout of the system. We have source. It has 25 meter head difference between water level in the source, that is river, to the field. So we are simply assuming that we are putting a pump which is lifting water from the source at a 5 meter lift depth, and it is delivering water to the field by using a 20 meter lift pipe or delivery pipe. In the field it is 200 meter by 300 meter. So we are dividing in number of conditions. Now you need to find out what size it should be. It is given here layout for 50 meter, which is coming after calculation. You can see here. So suction pipe is 8 centimeter in diameter. Delivery pipe is as well 8 centimeter. We will see how it is working. 8 centimeter in diameter. Then it is a main line which is supplying water. Then it is a lateral here. And from lateral it is connected with sub main. Sorry, it is sub main. This is main line. This is sub main here. And then we have laterals here for every plant, every field. How many laterals we will find out. And in each lateral, drippers are fitted there through a dripper tubing, or maybe on line itself. So this is basically layout which we are going to understand from this problem. Now, first to find out how much water it is required to irrigate and at what frequency, after how many days, to supply required amount of water to this plantation or to this field we have taken as an example here. So where to start? Simply, the first step is depth of water to be applied in one irrigation. How much it is? Water required is simply field capacity minus wilting point. This is basically bulk density of water and bulk density of soil, and bulk density of water should be divided to make this apparent specific gravity. Critical point is 80%. So difference or water required to make the soil at field capacity level is simply 20% of this difference. So 1 minus Cp, and depth is root zone depth, that is 1.5 meter. And to make this D in unit millimeter, it is multiplied by 1000. So depth of irrigation or net depth of irrigation required to make the soil to field capacity condition from now, it is 63 millimeter. But that is the net depth which we are supplying through irrigation system, which has a lot of losses. So let us take application efficiency into condition, that is 0.9 it is given. So gross depth of water or net depth of water to be pumped, it is simply coming to 70 millimeter. Now, after how many days we need to apply water, or how much time it will take to remove from water from field capacity to make this 80% critical point condition? So that is amount of water, it is 70 millimeter. Now, sorry, it is net condition, that is 63 millimeter. Net, that is pumped there, pumped from the source to make this 60%, that is net. So after how many days it will require to remove 63 millimeter of water from 1.5 meter root zone depth. That is our frequency of irrigation, simple idea. Peak ET is 8 millimeter per day. Let us say 2 millimeter per day. Here it is one more assumption that water may remove further or maybe lateral. Reason being, why it is? We are irrigating out of this total area only 40% area. So this soil is relatively unsaturated, or it has much less water than this 40% area. So there will be huge amount of loss of water, or it will move from this to this as well. So let us consider 2 millimeter per day is as well loss of water in this direction. So it makes a total loss of water per day from the area, that is 10 millimeter per day, that is ET of the crop. So now 63 millimeter water that is removed in a certain days or means period of time. So we need to make the frequency or re-irrigate the field again after so many days, we need to find out. So that is basically irrigation interval. So net amount of ET, that is 63, and per day it is removed 10 millimeter, sorry 63 millimeter, and 10 millimeter it is removed per day. So after 6 days we need to irrigate the field again. So frequency of irrigation is 6 days. Our interval of irrigation is 6 days. So every 6 days we need to apply water to the field condition 63 millimeter. But to pump the water to make this 63, it is 70 millimeter. Now let us go to system capacity design. So this is total 6 hectare area, which must be irrigated in such a way that within 6 days this whole 6 hectare area is irrigated once, and the 7th day it is again coming to the first part. So there must be six equal portions which are covered in 6 days. 1, 2, 3, 4, 5, and let us make one more. So it is 6 days. It is covering just one portion every day, and the 7th day it is again coming here. So 6 hectare. So 6 hectare area into 6 equal parts, each will become 1 hectare land. And assuming that fraction of the total area, 5 meter by 5 meter, it is the plant spacing, row and plant to plant. and 40% area it is irrigated. So we need to apply water to this 40% area only. So out of 1 hectare or total 6 hectare, only 40% area we need to irrigate. So assuming that fraction of the total area that need to be wetted is 0.4, 40%. How much is the effective area? Out of 1 hectare, 40%, that makes 4,000 square meter area we need to apply this water. Net amount we need to apply, that is 70 millimeter, or it is 0.07 meter, and time is 10 hours in a day, because this is just one part daily, and operational time we are assuming that it is 10 hours in a day. So that is 36,000 seconds. So we need to apply in this 4,000 square meter area 0.07 meter water in 36,000 seconds. So what will be the discharge rate in liter per second of the system? System capacity in that way will become to this area, this depth, and this is the time 36,000 seconds. That comes 7.8 liters per second should be the system capacity. And now to supply this much amount of water, we need to find out the lateral, mains and submain. So let us find out lateral, because that is at the last on which drippers are fitted. Laterals, for 1 hectare area, there are 20 laterals, means you have seen from the pump discharge point, it is main, then we have laterals, right? We have laterals, and from submains, and then from submain we have laterals. So it is simple area, that is 50 meter by 200 meter, that makes 1 hectare, and plant to plant distance is 5 meter, row to row distance is 5 meter. So if we have a lateral covering this 50 meter, submain 50 meter, and lateral every side we have, this is 100 meter this side, 100 meter this side, but at the last 2 meter we can not, reason being plant is here, not at the boundary. So it may be near about 98 meter. So how many to cover this 50? 10 this side, 10 this side, to make 20 laterals. So for 1 hectare coverage, there are 20 laterals, 10 on each side of the submain. This is submain. And length of the each lateral is 98 meter to cover this just 100 meter length of citrus plantation. So capacity of each lateral, we have 98 laterals, right? And 98 meter length, 20 laterals, and 7.8 liters per second need to be applied to this whole 1 hectare land. So 7.8 divided by 20 laterals, per lateral capacity will come 0.39 liters per second per lateral. Now emitters capacity, emitter discharge, we can find out net depth of water that is required, that is 0.07 meter. Bedded area for 1 tree, that is 5 meter by 5 meter and 40%, and time, that is in 10 hours. So it is simply, this is meter, this is square meter, and this is hours. So cubic meter per hour, that is simply coming 0.07 cubic meter per hour is the emitter discharge, per emitter discharge. That is simply 70 liters per hour per plant we need to apply. Since 1 emitter of 70 liters per hour capacity is very high capacity, so we are putting 2 emitters per plant that will provide 35 liters per hour each. And we are putting, this is plants, so 1 meter this side, 1 meter this side. So 2 plants are supplying 35 liters per hour to the single plant. So in this way, we can find out what is the capacity of emitter. So we are putting 35 liters per hour capacity emitter to supply the required amount of water to this plant in just 10 hours to cover 40% of the area that is assigned to this plant, that is 5 into 5 into 0.4 square meter. That is coming 10 square meter area we need to supply water. Okay, now it is design of lateral. Reason being each lateral have is 98 meters, so number of laterals for entire farm, because in 10 this side, 10 this side, so there are 6 portions, so 60 one side and 60 another side, there will be 120 laterals. Each lateral size 98 meter. Flow rate 0.39 liter per second we have seen earlier, calculated earlier. So lateral is a multiple outlet because every lateral has 98 meter lateral has high at least 20 outlets, and there are two emitters connected. So if it individually they are connected, so there are 20 outlets in each emitter. So lateral is a multiple outlet pipe with outlets, and hence F, if you recall this equation we used for a sprinkler and discussed in theory, the value of K if we are knowing, L Q to the power 1.75, D is the dia of lateral to the power minus 4.75, and F is the factor which is governing this multiple outlet pipe fraction condition. So we can find out the head loss for this lateral. And for F, because there are 40 outlets, let us see here. K value is 7.89 to the power 5. Pipe length, that is 98 meter, lateral size. Flow rate 0.39 liters per second to the power 1.75. Inner diameter of lateral we are taking 20 mm. F, that is basically multiple factor that can be adjusted for 40 here. So 40 outlets we are connected to each lateral, or 40 drippers are connected. So the value of multiplicative value of F is 0.376 we can use here. So total head loss in each of the lateral, that is 3.7 meter. Now submain, total number of submains for entire farm 6, because it is divided in 6, and each is of 48 meter because 50 meter is the size. We can cover by 48 meter to this hole to connect these laterals for submain. Flow rate is 7.8 liter per second. Submain is also a multiple outlet with 20 outlets, 10 lateral this side and 10 lateral this side. So there are 20 outlets. Diameter we are picking 8 meter. So we can find out what is the head loss by using the same equation, only F value will change. That is for 20 outlet it is coming 389 from the same table, and head loss in lateral it is coming 0.49 meter. Now it is design of main, maximum length of main, that is 200 meter of the field we are taking. Flow rate is same 7.8 liter per second that we need to provide, and it is not multiple outlet but it is single outlet that is connected to submain. So value of F becomes 1. Head loss we can calculate, that is coming 5.2 meter for a 80 millimeter dia size of the main line. Now total head required of the system, assume that head required at each emitter, or that is the farthest emitter, 0.6 kg per centimeter square, or simply 6 meter head of water. Bend losses, other necessaries, valves requires 1 meter head loss. So total head loss of the system, head required for the operation, that is minimum 6 meter. Frictional losses, lateral, submain, main, and then these fittings, 1, that makes 16.39 meter. Now it is pumping head, that is the condition. Next condition to select the pump, it is pump basically. We are taking 8 centimeter diameter GI pipe has a suction pipe as well as delivery pipe, and it is supplying 7.8 liters per second to 6 meter head per 100 meter pipe length, or 6 meter per 100 pipe meter length is the head loss there. So we can find out for different condition: suction head, head loss to suction side, delivery head loss to delivery side, velocity head, and system head we have already calculated here 16.39 meter. So if we are adding all, it will give the total head of the system. So it is calculation part, total head of the system, that is coming near about 43.013 or 43 meter. And discharge, that is 7.8 liter per second. So we can find out water horsepower that is required, discharge in liter per second, total head that is required 43 meter in meters divided by 75. So that is coming 4.5 horsepower is required to supply this discharge condition to this system, drip irrigation system. However, system requires some losses and efficiency becomes lesser than designed condition. So we are considering the efficiency of the system, drive efficiency, pump efficiency, and motor efficiency combined. It is only 0.75. So if we are dividing this efficiency with this net horsepower we have calculated, gross horsepower or required horsepower to operate this system satisfactory to supply 7.8 liter per second becomes 6 horsepower motor or electric motor we can put there to supply the water. In this way we can design. Yes, please.
Can we leave now, because from 11 we have test.
Where?
In next class, because from 11 to 11:30.
Just 2 minutes. I'm finishing. That's why I ask always come in time. So just 2 minutes. Let me summarize it here. So for application of fertilizer, we are using pressurized condition. Venturi it is used. We have a pressure tank where this fertilizer is stored, and then venturi is connected in this way, just like it is tank, it is connected through a venturi. Here venturi, it is control valve, and because of pressure difference it is meeting to the water line or supply line. So this is the schematic arrangement for the venturi in the system. So venturi injector, advantage, disadvantage you can read, and this is just end of the system design of drip irrigation system. So you have learned sprinkler as well as drip irrigation, which are coming under pressurized irrigation system. So if you have any query related to irrigation system design, conveyance design, water supply, soil water properties, somebody has asked if you have question, but whatever material I have given you can find out there, and books I have given in my first lecture, it is updated there or uploaded there. You can find out. And if you have any further query, you can ask me anytime. And from here, it is means sufficient for you in irrigation system, irrigation part. Drainage part from Monday onward, right time 9 to 10 to 11, same timetable. Professor Damodar Rao will take the classes. Is it okay? Can you tell me whether it is okay? Okay. So if you have any query anytime, you can ask me. Otherwise, you are free from irrigation portion. Now it is drainage portion, means removal of excess water. Any query? Say no if you do not have.
No, sir.
Okay. No, then sir. You are then go, because you have another test. That's why I have taken 2 minutes to summarize it. Okay, welcome. Next class will be by Dr. Damodar. Okay. Okay.
Excuse me, sir.
Yeah, please. Jyotiradit.
Sir, our end-sem exam will contain the syllabus up to the post-mid-sem or the entire syllabus?
Entire syllabus. End semester is always entire semester. It is not like post-mid. You have written already. You are third year, second year, means 5 examinations already.
Yes.
Maybe a few of online, but it is always from the total. So you are asking this question every semester to every teacher, that I know.
Sir, actually, in the the earlier classes, professor used to do some reduction of the syllabus. That's why.
There will be portion because 30% we have already asked there. 50% is remain from our side. Total makes 80% of the learning. 20% is the teacher's assessment. You know it all these conditions. So it will be substantial amount from the portion you have learned before say mid semester usually.
Yes.
Okay.
Thank you.
Okay, welcome. Okay, so go to the next class. You have test. See you.